Disney's Disneyland.
When you wish upon a star, makes no difference who you are.
Each week as you enter this timeless land, one of these many worlds will open to you. Frontierland. Tall tales and true from the legendary past. Tomorrowland. Promise of things to come. Adventureland. The wonder world of nature's own realm. Fantasyland. The happiest kingdom of them all. Presenting this week. Here to introduce you to this new series is Walt Disney.
In our modern world, everywhere we look, we see the influence science has upon our daily lives. Discoveries that were miracles a few short years ago are accepted as commonplace today. Many of the things that seem impossible now will become realities tomorrow. One of man's oldest dreams has been the desire for space travel, to travel to other worlds. Until recently, this seemed to be an impossibility. But great new discoveries have brought us to the threshold of a new frontier, the frontier of interplanetary space. In this Tomorrowland series, we are combining the tools of our trade with the knowledge of the scientists to give a factual picture of the latest plans for man's newest adventure. Here's Director Ward Kimball to tell you about it.
In working with engineers and scientists, we have found that there are many different opinions as to how we will eventually cross the space frontier. However, there's one point all of them seem to agree upon, and that is whether we use chemical fuels or atomic energy, it will be a rocket-powered ship that will finally take man into space. So, to set the stage for the part the rocket will play in the coming conquest of space, our artists have searched back through history and traced the rocket and various space travel ideas from their earliest beginnings. The first thing we found out was that the rocket is not such a modern invention after all. In fact, its history began way back in the 13th century. It was in China, to be exact, at the Battle of Kai Feng Fu. A little over 500 years later, Sir Isaac Newton explained this phenomenon by saying, "For every action force, there is always an equal but opposite reaction force." Sir Isaac's statement can best be illustrated by showing what happens to our pet dog when he sneezes. For every action, there is an opposite but equal reaction. This same principle applies when we light an ordinary skyrocket. Action, reaction. However, gunpowder is not the only propellant that demonstrates the action-reaction law. There was a time when steam was seriously considered as a means of rocket propulsion. Typifying this idea was Charles Golightly's aerial steam horse. Early inventors soon realized that steam rockets would be too heavy to fly, so they returned to designs utilizing gunpowder. These ideas made many successful flights, on paper. In 1865, Jules Verne fired the imagination of the world with his first book on space travel. It was called From the Earth to the Moon. Mr. Verne used a very interesting device in getting his heroes to the moon. He shot them through space inside an enormous artillery projectile. It was Verne's story that inspired George Méliès to create the first space travel motion picture in 1902. first man to associate space travel with the use of rocket power was Hermann Gonsfin. His idea was to have the rocket pull the ship instead of push it. This conception was quite unique, but only an inventor's dream. However, a few decades later, a real milestone in rocket history was passed when the American professor, Robert H. Goddard, introduced a liquid fuel rocket, which used gasoline and liquid oxygen instead of gunpowder. This small forerunner of our large present-day rockets actually rose 60 feet into a wintry New England sky. These experiments led to the founding of the American Rocket Society to advance the science of rocket propulsion. At the same time, the German professor Hermann Oberth wrote, "Theoretically, there is no limit to the size of a rocket which uses liquid fuel." In 1929, Oberth designed a giant rocket ship for the Fritz Lang movie, Frau im Mond. The Girl in the Moon. During the late 1920s and early 30s, we saw an era of feverish activity among the rocket experimenters. Almost every type of vehicle was adapted to rocket power. Here is the first successful flight of a rocket-powered airplane. Rocket-powered autos were fast, but presented quite a smoke problem. There were railroad rockets and nautical rockets. Some fired and some backfired. These early attempts met with varying degrees of success. Meanwhile, in Germany, a group of serious-minded engineers founded a new society for space travel and succeeded in building rockets which finally reached an altitude of 1/2 mile. Soon after this, the German Army established its own rocket program. The development of the first rocket missiles followed. This accelerated rocket program culminated in the creation of the forerunner of spaceships to come, the V-2. Even though there were a few mishaps, the V-2 emerged at the end of the Second World War as the most successful rocket yet devised by man. 75 of these captured V-2s were brought to our rocket proving ground at White Sands, New Mexico in 1945. Here, exhaustive studies and test firings were made to aid us in mapping our own newly created rocket program. It wasn't long before the sands of New Mexico shook to the roaring blast of the Viking, the Corporal, the Aerobee, and other American rockets. rocket firing is an awesome demonstration of tremendous power. I think we should find out how it works. One of the best authorities on this subject is the rocket historian, Willie Lay. Here Mr. Lay explains the operation of a rocket motor to some of the artists working on the picture.
This is an actual propulsion unit from a V2. And this strange-looking device is both the heart and muscle of a rocket, its motor. Now, all earthbound engines have to burn oxygen from the surrounding atmosphere. But the high-altitude rocket motor has to work in outer space where there is no oxygen. To overcome this, we carry a tank of liquid oxygen here. When burned with a fuel, in this case alcohol, it produces an intensely hot, torch-like flame that would quickly melt the motor. However, we cool the motor by first circulating the alcohol fuel around it, until this fuel finally reaches the point where it is sprayed, along with the oxygen, into the combustion chamber. When this steady flow of alcohol and oxygen is ignited, it produces a continuous explosion which blasts the rocket away in the opposite direction. Here again we have action and reaction. If this motor is placed in a streamlined hull with suitable controls, it can reach a high altitude in a very short time. The V2 rocket motor only operates 65 seconds to a height of 20 miles. But then the V2 has gathered so much speed that it will coast upward to an altitude of 114 miles before gravity begins to pull it back to Earth. Notice that the rocket does not nose over in the thin upper air, but it falls tail first until it re-enters the denser atmosphere where the air, acting on the tail fins, turns the rocket nose down. Early in 1949, space history was made when the payload in the nose of a V2 was a small rocket called the WAC Corporal. When the large V2 reached its maximum speed, the smaller rocket was ignited. This additional boost in speed enabled the WAC Corporal to set a new high-altitude record of 250 miles. This day marked the first time that a man-made object reached outer space. This was accomplished by using a double rocket, then secretly known as Project Bomber. However, we refer to it as a two-step or two-stage rocket.
Is it possible to build a three-stage rocket?
Yes, as a matter of fact, that's the next logical step. Here's a rocket I have designed that has 3 stages. It would stand about 70 feet high, or a little taller than the old V2. Here you can see the 3 sections, each one having its own rocket motor. If somebody will please make a sketch for me, perhaps I can explain how it will work. Good. Here we show our